20s. Welcome back. Today we're gonna go over some of the big concepts from chapter 4. Chapter 4, we're gonna deal with gravitational forces and gravitational fields. So here we go. So 4.1, we're starting off with really basic. So far, what we know mostly from Science 10 about gravity is weight. Gravity is the force that pulls down objects, let's say, that are on the surface of the Earth. So you learned how to calculate weight before in this course, and obviously in Science 10, just mg, where g is the acceleration due to gravity on Earth. We know it is a constant of 9.81 meters per second squared. We'll find out that, yes, it is a constant, but also it varies a little bit too. We'll talk about that. Gravitational mass. So when you put something on a scale, you're weighing it, you're determining its weight. But really, most of us, when we put ourselves on a scale, we're measuring our mass in kilograms. And when we're doing that, we're measuring our what we call gravitational mass. So gravitational mass is a mass measurement based on comparing the known weight of one object to the unknown weight of another object. So one of those old-fashioned balance scales there, measuring the mass of an apple. So let's say you've got your standard masses there, and let's say that's 100 grams, that's 150, or 100 grams and 50 grams, so you've got 150 grams there. And if it measures, if it balances out with the apple there on the other side of the scale, then we are saying then, oh, well, the mass of the apple then must be 150 grams. So when you're doing that, when you're comparing the unknown mass to a known mass, you're determining what is called the gravitational mass of the object. In that case, the apple, 150 grams. However, mass is mass. The term gravitational mass and inertial mass, two different terms, but whether you're talking about gravitational mass or inertial mass of the apple, still going to be 150 grams. So inertial mass goes back to Newton's laws, first law of inertia. Mass is the tendency of an object to resist acceleration. So in order to determine the inertial mass of an object, what you do is you essentially use the second law, F equals ma. And if you solve for mass, then it's force divided by acceleration. So what you do is to measure the inertial mass of an object, you put a known net force on it, push it, and measure its acceleration. When you divide the two, force that you exerted divided by the acceleration, you're going to get its mass. So obviously, like if you exert a force on an apple and that same force on a bowling ball, the bowling ball is going to accelerate less because its mass is higher, it's got more inertia. Okay. Describing gravitational force as a field. Now, this is a pretty important concept here in Physics 20. It's the first time that we are describing a field. A field is a concept that is used to explain what we call action at a distance forces. Forces between objects that are not in contact. So if I'm talking about apples and bowling balls and stuff like that, if I want to, exert a force on an apple or a bowling ball, I have to touch it. I have to push it or pull it or do whatever, pick it up. Whereas if you hold up an apple and you drop it, it experiences an unbalanced force down towards the Earth. But the Earth is not touching the apple. There is no contact there. So we would say that is action at a distance. Same thing with two magnets. Right, you have magnets attract each other, magnets repel each other. They can attract and repel each other without coming into contact. So action at a distance is that action is to exert a force at a distance, obviously with no contact. So to explain that, we would say, for example, for the Earth and the apple again, that the Earth is surrounded by what we call a gravitational field. A field, as it says, is a three-dimensional sphere of influence. And that influence is to exert, in the case of a gravitational field, a gravitational force. Field concept was developed by Michael Faraday, to explain electrostatic phenomena, so forces between electric charges, magnets, stuff like that. You're going to learn about that stuff in Physics 30. So a gravitational field surrounds any object that has mass. Magnets are surrounded by magnetic fields, and electric charges, positives, negatives, protons, electrons, stuff like that, are surrounded by electric fields. So we're going to teach you about gravitational fields in Physics 20, and then a lot of that concept you're going to learn this year is going to be carried over into next year when you learn about electric fields and magnetic fields. Okay, so to represent pictorially a field around an object, what we do is we draw field lines or lines of force. Now, normally when we draw arrows on a page in our physics book, we say, oh, those arrows represent vectors. And those are not vector arrows. They're different. They're called field lines or lines of force. They look the same because they're arrows and they point in a certain direction. However, here's the difference. For a vector arrow and for a field line, the direction that the arrow points or the direction that the field line points represents the direction of the quantity you're representing. So here, obviously, the direction of the gravitational field points towards the moon, points towards the Earth. However, the difference between a field line and a vector arrow is for a vector arrow, we represent magnitude by the length of the line segment. So small magnitude, short line, big magnitude, big line, or long line. Whereas for a field line, well, field lines are technically infinitely long. They don't have a length. We just stopped the field lines here in these diagrams just because we don't want to draw them, to the edge of the page. We just limit the size of them by just the size of our diagram. However, the way a field is represented in terms of the magnitude of the field is, like it says, how close together the field lines are. In other words, how dense they are. So we notice that here's the difference between the Earth and the moon. The arrows field lines are about the same length. However, we notice that we know on the moon that there's less gravity than there is on the Earth. We'll notice if you're on the surface of the Earth, notice how close these field lines are together. If you're on the surface of the moon, you've got field lines, but they're further apart. And we also notice as we move away from the source of the field here, whether it be the moon or the Earth, the field lines get further and further and further apart, indicating that the strength of the field gets less and less and less as you move away from the source of an object, or source of a field, I mean. So that same thing applies for next year when we start talking about electric fields and for magnetic fields as well. Okay, so gravitational field strength is defined as the gravitational force per unit mass at a specific location. So if you take your Fg equals mg formula, your weight formula you need to solve for gravitational field strength, you get gravitational force per unit mass. And notice it says test mass. We'll talk about what that means. But if I want to test the direction of a field, like say the direction of the gravitational field in this room, you take a pencil and it's in Earth's gravitational field, and I let it go, and I would say, oh, well, the direction of that field is down because that pencil was influenced to drop down. This is what it says on your data sheet. Acceleration due to gravity on Earth, 9.81 meters per second squared, or gravitational field strength near the surface of the Earth, 9.81 newtons per kilogram. Newtons divided by kilograms ends up giving you meters per second squared. But when we say gravitational field strength, we mean force per unit mass. So a 1 kilogram object on the surface of the Earth would experience a gravitational force of 9.81 newtons. A 2 kilogram mass would experience double that force, but still 9.81 newtons for every kilogram. And as it indicated on the diagram on the previous slide there, where the field lines get further and further and further apart, as you move away from, let's say, Earth as an example of a source of a field, the amount of gravity or the gravitational force that is exerted on you per unit mass decreases in strength. And we can see that by this relationship right here. We see that we've got a magnitude of gravitational field strength as a function of the distance from the center of the Earth. And we notice that it decreases as the inverse of the square of the distance. This is an inverse square relationship.
Okay, so we're going to go over a few examples here of just some real quick and easy proportionality type problems. So this is the concept check from your textbook. What happens to the magnitude of the gravitational field strength if the distance between the two objects decreases by a factor of 4? Okay, well, let's see. For A, the gravitational field strength varies inversely as the distance between the two objects. R decreases by a factor of 4. So what that means is it's 1/4 the distance. All right. So what you do is to figure out the effect on the gravitational field strength, you put in a factor of 1/4 for the distance. And notice we're not using equal signs here. We're using a proportionality sign. That alpha sign is used to represent proportionality. So 1/4 squared is obviously 1/16. And 1/16 is, when you take the reciprocal of that, is equal to 16. So what happens is the gravitational field strength increases by a factor of 16. You get 16 times the gravitational field strength. For B, R increases by a factor of 2. So it's 2 times R. So what we do is that same relationship. How does that affect the gravitational field strength? If R doubles, then the gravitational field strength decreases by a factor of 1/4. So you've got 1/4 the amount of gravitational field strength. For C and D, what if the test mass doubles and what if the test mass is halved? Well, it's I wouldn't say a trick question, but test mass is, the mass that you test the gravitational field strength with. So if you drop a pencil or an apple or a bowling ball, it doesn't matter. You're changing the test mass. Whether you're dropping a pencil or a bowling ball or a filing cabinet or a car, the amount of force on each thing is going to change. So the amount of force on a pencil is much less than the amount of force on let's say a car, obviously. But whether you're talking about a pencil or a car, the gravitational field strength is unaffected by the test mass. So on Earth, remember we said the average gravitational field strength, 9.81 newtons per every kilogram. So when we change the test object, whether it be a pencil or a bowling ball, the gravitational field strength is still the same, 9.81s for newtons per kilogram. So that means then that for C and D, just write this down, changing the value of the test mass does not affect gravitational field strength. It's still the same number of newtons for every kilogram of mass.
Okay, so that's it for 4.1. You keep on watching the video if you want, or at this time, just pause the video, take a few minutes to read those pages, try those questions for some practice and come back when you're ready. Section 4.2, Newton's law of universal gravitation. So we ended off the last section talking about that inverse squared relationship for magnitude of gravitational field strength as a function of distance away from the source of the field. Gravitational forces behave the same way. So we take a look at this diagram here. We've got the Earth as the source of a gravitational field, and we're going to talk about, I guess this is a satellite, looks like a paint can or something like that, on the surface of the Earth. When it's on the surface of the Earth, it is 1 Earth radius away from the center, and it's got a weight of just Fg. Doesn't matter what it is, doesn't matter how many newtons. Let's say now you launch your satellite in orbit, and it's in this first orbit right here. The distance away from the center of the Earth is 2 Earth radii now. So what you've done is you've doubled the distance from the center of the Earth. When you go from the surface to this first orbit, you go from 1 Earth radius to 2 Earth radii away. When you double the distance, if this increases by a factor of 2, then the gravitational force, or the weight of the satellite there, decreases by a factor of 1/2 squared, or 1/4. So notice as you've got 1/4 the weight. Same thing if you go to an even higher orbit, we go from 1 to 2 to 3 Earth radii away from the center of the Earth. So compared to when it's on the surface, you've now tripled the distance away from the center you are. Well, the gravitational field strength, or gravitational force, also then on the satellite, or the weight of the satellite, would decrease by a factor of 1/9, 1/3 squared. So again, it's that inverse squared relationship. Okay, so in general, the gravitational force between any two masses can be shown by the following formula. Fg equals g m1 m2 over r squared. So far we're kind of limited to discussing gravitational force as force on an object that is on the surface of the Earth. However, we know that there's satellites orbiting the Earth. The moon is a satellite of the Earth, and it goes around and around. Obviously, it is attracted to the Earth. That is a gravitational force. You've got a force between m1, the Earth, and m2, the moon. Also, planets orbit the sun in our solar system. So Earth orbits the sun. M1 is the sun, M2 is the Earth. You've got a gravitational force of attraction there. So gravity is a relatively weak force when you talk about the 4 fundamental forces of nature that we talked about before at the beginning of dynamics. But it actually exists between any two masses. So your textbook and your calculator, they both have mass. They're a certain distance apart. They are actually attracting each other with a very small gravitational force. So gravitation, or gravity, is not just a force that exists that like big masses generate, like a planet or something like that. Actually, any mass has its own gravitational field. So all mass attracts other mass. So your pencil and your calculator are attracting each other. Your computer and the moon are attracting each other. This coffee cup and my printer over there, they're attracting each other via gravity. Now, your textbook and your calculator don't like come together like two magnets that they're attracting each other. So gravity is a very weak force. However, we're going to expand our view of what gravity is. Notice I keep using the word gravitation to imply that it is a force between any two masses anywhere in the universe. Okay, so before I go on, that gravitational constant, it's on your data sheet. It's not something you need to memorize. It's probably by the time you're done going through these questions, you'll probably just memorize it by accident, just like you memorized, 9.81 is the acceleration due to gravity. It is a very small number. It it is 6.67 times 10 to the negative 11. 6.67 times 10 to the negative 11. So negative 11, that's a lot of zeros after the decimal place, right? So 0.00000, like 10 zeros, 667. So that's a very small number. So if we have like a 1 kilogram mass and a 1 kilogram mass separated by a distance of 1 meter, if everything in this formula is 1, 1, and 1, and this gravitational constant is 6.67 times 10 to the negative 11, that is a very, very, very small force and something that we can't even measure. But how do we know that that number is 6.67 times 10 to the negative 11? Well, in order to do that, we're going to learn a little bit about what we call the Cavendish experiment. Now, I'm going to explain it in brief here. I'm going to insert a YouTube link to a video that I'd like you to watch that explains the Cavendish experiment in a little bit more detail, because it's just better. It's got the apparatus there instead of me showing, like static images and me waving my hands around and stuff like that. It's a much better representation. But essentially, here's what we have. Henry Cavendish, a long, long time ago, used an apparatus very similar to this. Obviously, it was back in the 1700s, so he didn't have lasers and stuff like that. But he used a torsion balance. Torsion balance is a device used to measure very small forces. So here you've got a large mass, mass M, another large mass, mass M. So they might be like something very massive, like a cannonball or something made out of lead or something like that. And on the end of a rod, you've got relatively small masses there and there. And that rod is hanging from what you call a torsion fiber. So what will happen is there will be a force of attraction between this mass here and the big mass there. There'll be a force of attraction between this small mass and this big mass. And what that'll do is it's going to cause that wire to twist. And when it causes that twist, that is a way to measure the force or get an indication of the force. A large twist means a large force. A very small amount of twist means a pretty small force. So in order to measure or determine the gravitational constant, big G there, you need to know, we'll go back to this. In order to determine this, you need to know the force, you need to know the two masses, and you need to know the distance. Well, for that Cavendish experiment, it's pretty easy to know what those masses are. Like the big mass might be, 50 kilograms, and the small mass might be 1 kilogram, whatever. The distance between them, that's pretty easy to measure. Just use a ruler, so to speak. The amount of force measured, well, for a modern experiment, the amount that the wire twists can actually be measured. It is called a torque and a twisting force, and then there's an apparatus where you've got a dial and you can actually measure it. But as far as we're concerned, we're just going to simplify it a little bit. We're going to say that the more the wire twists, the greater the value of that gravitational force. So the amount of twist on the wire is used to determine or is related to the amount of gravitational force. So again, in order to determine G, you need to know everything else in that formula. The two masses, easily known, you can measure those. Distance between them, easily known, you can measure those. And we're going to say that the gravitational force is related to the amount of twist on the wire. More twist, more force. Okay, so just go watch the YouTube link, and there's more details in terms of the Cavendish experiment. But we're just going to simplify it as far as we're concerned for just in Physics 20, especially in our conditions that we're learning in now.
The gravitational force between the two masses pictured below is 1.40 times 10 to the negative 7 newtons. Determine the distance between them. Okay, well, this one's pretty straightforward. We've got our formula for Newton's law of universal gravitation. We're given the force and we're given the value of the two masses, and you want to solve for the distance between them. So what you do is you rearrange the formula and you solve for r, distance between them. So gm1 m2 over fg. So 6.67 times 10 to the negative 11 Newton meters squared per kilogram squared. Mass 1, 10.0 kilograms. Mass 2, 15.0 kilograms, divided by the gravitational force between them, which was given as 1.40 times 10 to the negative 7 newtons. And we take note that, yeah, that is a really small force. 10 kilogram mass and a 15 kilogram mass don't generate very much force between them because gravity is such a weak force. So anyway, you end up getting 0.267 meters, or just to put it in centimeters, 26.7 centimeters apart. So those are pretty everyday kind of, reasonable average masses that you can think of. Like, you know about how much 10 kilograms is. It's about 22 pounds, and 15 kilograms is whatever it is. And then, 27 centimeters apart, you can kind of picture that. That is a really, really, really small force. Okay. Now, using proportionalities to solve gravitational problems. So this is using, instead of an equal sign, we're going to use an alpha sign. Alpha, Greek letter alpha, used to express proportionality. So objects A and B exert a gravitational force of 3.50 times 10 to the negative 9 newtons on each other. Determine the gravitational force between them when the mass of object A is doubled. Okay, so let's see. Here's our formula. Everything is unchanged except for the mass of object A. All you're doing is you're doubling the mass of object A. So you want to find out what effect changing this has on that. So what we do is we see that, okay, well, in our formula, um, both values are in the numerator and they're on opposite sides of the equal sign. So that tells us that that is a direct proportion. The gravitational force varies directly as the product of the masses. In other words, directly in this case is just ma. So if you double one of the masses, you're putting in a factor of 2. That means you're going to double the amount of force. So the final gravitational force is 2 times that initial gravitational force. So initial gravitational force, 3.50 times 10 to the negative 9 newtons. Doubling one of the masses will double that force to 7.00 times 10 to the negative 9 newtons. Okay, a couple more. The distance between the two objects is decreased by a factor of 1/3. So once again, there's our relationship between the masses and the distances and stuff like that. But now what we're doing, we want to find out the effect of changing r has on the amount of gravitational force. Well, from before, we remember that that is an inverse squared relationship. So the distance between the two objects is decreased by a factor of 1/3. So now we've got 1/3 the distance, 1/3 times r. So what we do is we plug in 1/3 on the denominator there. So we get, well, let's see, 1/3 squared is 1/9, and the reciprocal of 1/9 is obviously 9. So that means then that the gravitational force is increased by a factor of 9. So 9 times 3.5 times 10 to the negative 9 newtons. Oh, you know what? Distance between two objects decreased by 5. I forgot to multiply that out. So let me do that right. 9 times 3.5 times 10 to the negative 9. And you get 3.15 times 10 to the negative 8. All right. Last one. So we're changing 3 things now. The mass of object A is doubled. The mass of object B is tripled. And the distance between them is doubled. All right, so what we're doing is we're changing both masses and we're changing the distance. So changing 3 things at the same time. So mass of object A is doubled, we put in a factor of 2. Mass of object B is tripled, put in a factor of 3. And the distance between them is doubled, put in 2. So we end up getting 2 times 3 is 6. 2 squared is 4. So the gravitational field strength changes by a factor of 6 over 4, or gravitational force, I mean, changes by a factor of 6 over 4 or 3 over 2. Doesn't really matter. You don't have to like reduce the fraction, but just did it out of habit. So that means that the final gravitational force is 3/2 of the initial gravitational force. So again, we have that initial gravitational force, 3.50 times 10 to the negative 9 newtons. And when you multiply that out, you get 5.25 times 10 to the negative 9 newtons.
Okay, so that's it for universal gravitation. There's some pages for you guys to read and a few questions for you guys to try. So pause the video. I would recommend go ahead and doing that, coming back and finishing the rest. Or you can just keep on watching, whatever. I'm just going to pause. Okay, so last but not least, 4.3, relating gravitational field strength to gravitational force.
We have our 2 objects here. We have the Earth, we'll call that ME, call this MM for mass of the moon. So we can express the gravitational force between these 2 masses using Newton's law of universal gravitation. No problem. Okay, so the Earth and the moon are attracted to each other. The moon experiences a gravitational force that pulls it towards the Earth. Well, we can also write that force as a product of the mass of the moon times the gravitational field strength at that location. So on the surface of the Earth, we know right here, G is 9.81 newtons per kilogram. But at this location, it's going to be less than that, whatever it is. But there's still a gravitational field at that location. So what we can do then is okay, well, if these 2 formulas represent that same force, what we can do is we can set them equal to each other. And what what we notice is that, well, we can divide both sides by mass of the moon. That cancels out, and we're left with this. Gravitational field strength at that location is g times the mass of the Earth divided by the distance between the centers of the two objects, in this case, the Earth and the Moon.
So we use this formula to calculate the gravitational field strength when we're given information about the source of the field. So the mass of the object that is generating the field, we call that the mass of the source. And g, same gravitational constant from before. And r, distance from the center of the object that is generating the field. That is really important. Not the distance from the surface of the object, but distance from the center of the object that is generating the field. In your textbook, when you guys are doing some word problems, I just wanted to call your attention to this table on page 218. It gives you some masses and radii for different celestial bodies in your solar system, the sun, Earth's moon, and all the planets. So the author may ask you to, do a calculation involving Mars or something like that, and they don't give you the information for Mars in the word problem, unfortunately, so you have to go look this up on page 218.
The Hubble Space Telescope orbits Earth at an altitude of 569 kilometers. Determine Earth's gravitational field strength at that height. Okay, so the distance from here to here, we'll call that d. That's 569 kilometers. But we remember, we want to use not the distance from the surface of the Earth to the satellite. We want to use the distance from the center of the Earth to the satellite. This whole entire distance from there to there, that is r. Oops, got a little neater. So in our formula, g m over r squared, r is the distance between the centers of the objects, not just between the surface of the two objects. Okay, well, what we're going to do is we'll find out what that is. What we have to do is we have to add the radius of the Earth. Now, the radius of the Earth, that's in your data sheet. So you could just look that up. So the whole entire distance, r, is the distance from the surface to the satellite plus the radius of the Earth. So 569 kilometers would be, in terms of meters, 5.69 times 10 to the 5 meters. Add the radius of the Earth from your data sheet, 6.37 times 10 to the 6 meters. And that whole entire distance is 6.939 times 10 to the 6 meters. Okay. So then we can plug in our value of r into our formula. So we have gravitational constant, 6.67 times 10 to the negative 11. We have the mass of the Earth. This is also in your data booklet, or in your data sheet, I mean, your booklet. 5.97 times 10 to the 24 kilograms. Divided by our distance that we got from our previous step, 10 to the 6 meters squared. And we get the value at that location of 8.27 newtons per kilogram.
Okay, so keep on saying that the average acceleration due to gravity on the surface of the Earth is 9.81 meters per second squared, or the average gravitational field strength is 9.81 newtons per kilogram. But as we've learned about, as you get further away from the center of the source of a gravitational field, in other words, the center of the Earth, the value of the gravitational force on you and the gravitational field at that location actually changes. So the Earth is actually not a perfect sphere. It actually, as it rotates, it actually bulges at the equator a little bit. So if you're standing at the equator, you're a little bit further from the center of the Earth than if you're at the poles. The Earth is actually kind of squished a little bit, if you could believe it or not. It's not much. Also, too, there's a big difference in terms of altitude as well. So you can have, you can be standing at sea level, for example, on the beach, or you can be top of a really high mountain or something like that at a high elevation in Denver or something like that. The gravitational field strength is different in Denver than it is at the beach in Vancouver, just because of your elevation. You're further away from the surface of the Earth the higher you get up. And you might be thinking, 9.81, maybe it's like 9.80 or 9.82 at the most. It varies. Well, it varies actually quite a bit. At the equator, around 9.77 newtons per kilogram, and if you're at the poles, around 9.84. So that's a bit of a variation. We just use 9.81 as an average, however, for the surface of Earth. Okay, so there's some questions for you guys to practice, and some pages for you guys to read. We're almost done. Last thing, true weight versus apparent weight. Okay, so let's say you're standing on a scale in an elevator for some reason. It's a cool thing to do if you're in a physics class. And if whether you're standing on a scale or an elevator or just in your bathroom or something like that, it's going to, the gravity's going to pull you down onto the scale, and the scale will read your mass, or in other words, it's measuring your weight, but it'll tell you how many kilograms you are. But let's say you've got a Newton scale here. So you've got a student standing on a scale, and that scale is at rest. Well, that student then has a weight as measured by the scale of 600 newtons. So that we would call the student's true weight. If the elevator is either at rest or moving at a constant velocity, the forces acting on that student and on the scale and on the elevator therefore must be balanced. So the normal force pushing up on the student from the scale is going to be equal and opposite to the gravitational force, that true weight. So this scale is going to read 600 newtons. However, what if the elevator then starts accelerating up? Well, what will happen then is that scale is accelerating up into the student and is pushing the student, and the forces are unbalanced. Well, notice what happens there. The scale actually reads, it jumps up a little bit. The student's true weight, the student's mass times acceleration due to gravity, mg, has not changed, 600 newtons. However, the scale reads 750 newtons. We call that reading the student's apparent weight. It is not, their mass hasn't changed and the acceleration due to gravity hasn't changed, but because the scale is accelerating up, the apparent weight of the person is now increased 750 newtons. What if then the elevator accelerates down? So you get on the scale, you're on the lobby of a big building, and you press up, and then while this elevator is accelerating up, the reading on the scale would increase a little bit. And while let's say you're traveling up at a constant speed, just ignore that. While you're traveling up at a constant speed, that scale would then read 600 newtons because you're moving at a constant speed. But then when you reach the top floor, when the elevator is going to stop, it's going to slow down. So what will happen is that the scale will drop a little bit. So your apparent weight is a little bit less than your true weight. So what that looks like in a word problem is next.
A 63.0 kilogram student stands on a scale in an elevator while the elevator is accelerating upward at 1.40 meters per second squared. Determine the student's true weight and apparent weight at this instant. So the apparent weight is going to be what the scale reads, and the true weight, it will never change on Earth here, because remember, true weight is just equal to student's mass times the gravitational field strength. So 63.0 kilograms times 9.81 newtons per kilogram. And the student's true weight will be 618.03 newtons. I'm going to round it off to 618 newtons. So there's your true weight. True. Okay. Now to get the student's apparent weight, what we're going to do is we're going to draw ourselves a free body diagram of the student. Okay, so here's the student. They are accelerating up. Whoa. So that means that the force pushing up, which is a normal force exerted by the scale, that's what we're trying to find. So that's going to be the reading on the scale, is greater than the student's weight. So notice I drew that arrow longer. The normal force is longer than that gravitational force, indicating unbalanced forces. And again, from before, we have that 618 Newton force like that. Well, we're given the acceleration of the student. The student is accelerating upward at 1.40 meters per second squared. So what we can do is we can use our second law of motion to determine the unbalanced force or net force acting on the student. So mass times acceleration, 1.40 meters per second squared up. And we get an unbalanced force of 88.2 newtons up. All right. So we then can write an expression for that net force based on the free body diagram. Remember, net force is the vector sum of the forces acting on the object. And here we've got two forces. And we can use this to then solve for the normal force. Net force minus the weight. So we have net force, again, 88.2 newtons up. The weight is 618 newtons down, and we'll just use, like I use in my calculator, but I'll write it out, all the decimals from our previous calculation, 618.03 newtons. But by the time you round it off, you end up getting 706 newtons. So that normal force pushing up on the student is 706 newtons. So that means that's going to be the reading on the scale. Their apparent weight is therefore 706 newtons.
Weightlessness. So what if you've got an object that is in orbit? You've all seen footage of, astronauts on the space station or something like that. They appear to be weightless because they're floating around. And you might think, and a common misconception is that, oh, well, the reason why they're floating around is because they're so far away from Earth that there's no gravity out there. But if you think about it, well, if there's no gravity there, then how come the satellite keeps on orbiting the Earth? How come if it's got inertia, how come it doesn't just fly off into space? It's held there by gravity. There's plenty of gravity. Like the space station orbits, of the order of, I can't remember. Let's say, I don't know, a satellite orbits like of the order of 500 kilometers. Let's say. So if you think about 500 kilometers height above the surface of the Earth. And if you extrapolate that to like a 500 kilometer distance, on the surface of the Earth, like that's maybe, from Edmonton to I don't know, Calgary, like all the way down to the southern border of Alberta, let's say, for example. It might be about 500 kilometers. So relative to the size of the Earth, that's actually a very small distance. So why are the astronauts floating around? Well, here's why. So a satellite is able to orbit the Earth because of the shape of the Earth. The Earth curves away from the satellite. So if we imagine, let's say here's a cannon on the top of a really, 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 really tall mountain, and you fire a projectile from that cannon and it flies out horizontally and it drops also a little bit in terms of its parabolic trajectory we learned about in projectile motion. Well, if you fire out a cannon at a certain speed, it'll follow that parabolic trajectory like that. If you have an increased speed, it's going to travel further along the surface of the Earth before it hits the ground. But notice the Earth between points A and B is actually curving away because the Earth is a sphere. So if we were to fire a projectile at an exact velocity where the amount that it drops is exactly equal to the amount that the Earth curves away, it'll always fall towards the surface of the Earth, but never hit it because the Earth is curving away. So let's say, for example, you're on the top of a really tall mountain and you fire a projectile out and it's going 600 kilometers per second, like really, really, really fast. So it's going to travel 600 kilometers in 1 second. And what'll happen is it'll drop, let's say, I don't know, how far does an object drop in 1 second? Like say 2 meters or something like that. So it's going to drop 2 meters in 1 second. Well, if it's in orbit, when it travels that 600 kilometers, that Earth is actually going to curve exactly 2 meters in that 1 second. Exactly the distance that that object drops that's in orbit. So that's how orbit is achieved. And there's a couple YouTube videos that I'd like you to watch that demonstrate that exact thing. Like you've seen movies, right? For example, Apollo 11 or sort of Apollo 13 or something like that, where astronauts are floating in orbit. You can actually do that in an airplane. And watch the video. It's really cool. All right, so that's the end. So notice we went over all of chapter 4, sort of in one video, because really all those concepts are pretty closely related. Gravitational field, relating that to gravitational forces. So that's it for today. See you later, Physics 20.